again. Okay, so what is a probability? We have the idea of a probability model. Because everything we have so far, all we can do is we can say, well, we have a probability experiment. We could roll 2 dice. We could define various events, which are subsets of sample space. We could look at how many outcomes are in the sample space, how many outcomes are in each of the events. But we need an idea to predict what the likelihood is, how some things happen more often than others. And so that's from experience. That's the statistics. We could do the statistics. So the probability model assigns a fraction to every event. So it's not a fraction assigned to an outcome. It's a fraction assigned to an event. And what's going to happen is that fraction is going to be related in our classical model of probability that we're going to build to the number of items, the number of outcomes in the subset. So we're going to be doing counting in order to do our probability model. So what is a probability model? Well, it is an assignment of a fraction to every event. Let's look at the text to get so I get this right. So if we come through here, we have the idea of probability in chapter 8, which just deals with probability experience. We have the definition of an outcome, sample space, an event. We have simple events. A simple event is an event for an experiment that just contains one outcome. Yeah, we talked about mutually exclusive events, and we'll go and do some of these exercises in a little bit. So a probability model is an assignment of a fraction to every event like this. So the probability of an event. The probability of an event for a probability experiment is a number between 0 and 1 inclusive, and we'll name it probability of the event. So it's always going to be a number between 0 and 1. And then we're going to require that the probability that the number assigned to the empty set is 0 and the probability assigned to the sample space is 1. So let's think about that. Okay, so we always have to assign the probability, the number 0, to the probability of the empty set. Well, this means, so a probability of 0 means is impossible, right? The empty set never happens. It's like the impossible event. So it's like, whereas on the other hand, the probability of the sample space, so this one never happens. Well, the probability of the sample space size is 1. Well, if you have an experiment, an idealized experiment of tossing a coin heads or tails, it always comes up heads or tails. So this always happens. So 1, because of this sort of default situation, is that the closer the probability to 1 is, the more likely it will happen, and the closer it is to 0, the less likely it will happen. Okay, so we don't have to assign, like if we had a sample space for a coin of heads and tails, we can assign, for example, it might be that the coins aren't fair, that they aren't evenly balanced. So we could assign, say, what are the events? Well, the events are the simple event H and the simple event tails, as well as S, and we already have S in the sample. So we only have to assign the events of H and T. So the probability of the end here, we could make it, say, 3/4. Okay. Well, there's a problem. We can't randomly, there's some restrictions on the numbers that we can assign to the events. We can't just randomly assign this 3/4 and then like assign this also 3/4. And the requirement is, there's some requirements to make a valid probability model. And one of the requirements is the probability of all the simple events have to add up to 1. So for this case, if the probability of heads was 3/4, we must set the probability of tails to be 1/4, because the probability of heads plus the probability of tails has to equal 1. So 3/4 plus 1/4 is 1. So there's, and the same thing would happen for dice, in which we would assign numbers to one, fractions between 0 and 1 to different events. Okay, now this one doesn't have it. This sample space only has simple events, and so this is what we have so far. But there's a problem because, well, we're going to get to so let's start with this. This is this extra piece here, number 4. The probability of any union of mutually exclusive subsets equals the sum of the probabilities of those subsets. So let's look at the coin, where the sample space is 1, 2, 3, 4, 5, 6. Well, so I could have the event 1, 2 that has this, and the probability of E1, 2, and the probability, say, of 3, 4 is going to have the probability E3, 4. Well, this says that any union of mutually exclusive subsets equals the sum of the probabilities of those subsets. So what's going to have to happen is the probability of, because E1, 2 equals E1 union E2. It's the probability that it's the union of the event where you just had a 1 and just had a 2. So the probability of E1, 2 has to equal this. And because of this requirement that these are mutually exclusive subsets, there's no elements in common. So this one has to, so I can't freely choose all the probabilities of different events. What I can basically freely choose is the probabilities of the simple outcomes of 1 through 6. Then I can build up everything else by means of this rule. So if I assign probabilities that satisfy these rules, I have a valid probability model. And so that's what we want to do that. And maybe we can do is slow down here a little bit and go back, and then we will look at some of these exercises. Okay.